first order kinetics, and we'll do a brief review of some of that. And we're going to talk about second order kinetics today. We're going to come back and talk about chemical equilibrium, which is something I love to do to review things that we've talked about before. And we're going to start in on reaction mechanisms. So I thought I would mention, some of you may have seen the activity in the Infinite Corridor, but today is World AIDS Day. And today, a lot of the compounds that are being used to treat HIV were actually designed based on making inhibitors to enzymes. And so to design those pharmaceuticals, people had to understand the reaction mechanism of the enzyme. And enzymes, of course, are catalysts in the body. So knowledge of what medical individuals needed to know to design these inhibitors to treat HIV are actually a lot from this unit that we're going to be talking about. So we'll be talking about reaction mechanisms. And we're also going to be talking about enzyme catalysis, which were key points in being able to come up with some of the current treatments against HIV. All right, so just a little review from last Wednesday. We talked about first order half-life. We talked about first order kinetics. We came up with an integrated first order rate law. And we also talked about half-life. And you told me last time that an example of first order half-life is radioactivity, which we're going to be talking about today. So just a little review from last time. You have your first order integrated rate law. And the half-life is defined as the time it takes for half of the original material to go away. And the half-life is abbreviated T a half. That's the symbol for half-life. So the time for half of the original material to go away, if you plug original material divided by 2 in there, then the original material, A to the O for original, drops out. And you come up with this equation of the natural log of a half equals minus k t a half. And k is, of course, our rate constant. And so then we can take the natural log of a half, and we get a value. Rearranging that, you get half-life equals 0.6931 over k. And so you told me last time for this plot for first order half-life, each half-life, half of the original material goes away. So one example of a first order half-life process is radioactive decay. And the reason why this is a first order process is because the decay of the nucleus is independent of the number of surrounding nuclei that has been decayed. So it's independent of the original starting concentration. And since it's independent, you notice that's a blank in your notes, since it's independent, then that makes it a first order process. So we can apply first order integrated rate laws to radioactive decay. So here are some of the equations we had last time. We had, this is a different expression of the first order rate law, where the material, concentration of material A at some particular time equals the original concentration e to the minus kt, where you have your rate constant and the time that has elapsed. And we also just talked about first order half-lives with this equation here. So we can use those same equations, but often you don't see it in terms of concentration of A. You usually see these expressions in terms of either the number of nuclei or a different A, which is A for activity. So instead of concentration, we're talking about the number of nuclei that have decayed, or capital N. So we can write the same expression, but now using N instead of concentration of A. Same thing, number of nuclei equal the original number of nuclei, e to the minus kt, where k is our rate constant, or in this case, decay constant, and t is time. So with chemical kinetics, we're usually talking about the change in concentration of things over time. But with nuclear kinetics, we're talking about the number of decay events, the number of nuclei that have decayed. And so here, with nuclear kinetics, we measure these events using a Geiger